The universe, at the most fundamental level, may not have definite properties until something forces it to choose. Not we don't know the properties until we look the way. You don't know what's in a wrapped present until you open it. The properties may not exist until the act of measurement creates them. The present is empty until you open it. There is nothing inside. The act of opening generates the gift. This is not a metaphor. This is the central claim of the Copenhagen interpretation of quantum mechanics, the interpretation taught in every physics department in the world, used by every working physicist, confirmed by every experiment ever performed. And 100 years after its discovery, no one knows why it is true. No one knows what measurement means at the fundamental level. No one knows where the boundary lies between the quantum world of possibilities and the classical world of definite outcomes. And no one, not Einstein, not Bohr, not Feynman, not any of the greatest minds of the 20th century, has been able to explain how or why the act of observation forces the universe to make a choice. This is the measurement problem, the deepest unsolved problem in physics, and what it reveals about the nature of being, about what it means to exist, to observe, to be real, is stranger than any claim about quantum consciousness or manifesting your reality. The real physics does not tell you that your thoughts create reality. It tells you something far more disturbing, that reality may not be fully real until it is measured, and no one knows why. Let me start with the experiment that started everything, the double-slit experiment, because this is where the common understanding and the real physics diverge, and the divergence is everything. Here is what most people believe about the double-slit experiment. You fire particles, photons, electrons, atoms at a barrier with two slits. If you do not observe which slit the particle goes through, it behaves like a wave and creates an interference pattern on the detector screen, alternating bands of light and dark, the signature of wave behavior. But if you observe which slit the particle goes through, the interference pattern disappears. The particle behaves like a particle going through one slit or the other, not both. Observation changes behavior. Consciousness collapses the wave function. Your mind shapes reality. Here is the real version, and the real version requires you to understand what observation actually means in physics, because it does not mean what you think. In the double-slit experiment, observation does not mean a conscious being looking at something. It means physical interaction. To determine which slit a particle passes through, you must interact with it typically by shining a photon on it, or placing a detector near the slit that exchanges energy or momentum with the particle. This interaction, this physical exchange of energy, is what destroys the interference pattern. Not consciousness, not awareness, not intention. Physical interaction. The photon you used to see, the particle has kicked it, changed its momentum, altered its quantum state. The observation is not a passive act of witnessing. It is a physical intervention that changes the system. This is the standard explanation. It is taught in every quantum mechanics textbook. It is the explanation that most working physicists would give you if you asked them at a conference. And it is as far as it goes correct. But it is not the whole story. And the part it leaves out is where the real mystery begins. The standard explanation works perfectly for cases where the observer is a physical detector, a photon counter, an electron microscope, a piece of photographic film. In these cases, the observation is clearly a physical interaction, and the destruction of interference is clearly a consequence of energy exchange. No mystery, no consciousness required, just physics. But the standard explanation has a problem. A deep, unresolved, genuinely disturbing problem called the von Neumann chain, named after the Hungarian-American mathematician John von Neumann, one of the most brilliant minds of the 20th century. who identified it in his 1932 book, Mathematical Foundations of Quantum Mechanics. The problem is this: the equations of quantum mechanics do not distinguish between the detector and the thing being detected. The detector is also made of atoms. The atoms in the detector are also quantum objects. They also obey the Schrödinger equation. They also exist in superposition. When the particle interacts with the detector, the equations say that the particle and the detector together enter a joint superposition. The particle went through slit A, and the detector registered slit A, plus the particle went through slit B, and the detector registered slit B. The superposition is not destroyed by the detector. It is merely extended. The detector is now in superposition 2. And if you add a second detector to observe the first detector, the same thing happens. The second detector enters the superposition as well. And a third detector? Same. And your eye, which is also a detector, also made of atoms, also governed by quantum mechanics? Same. And your brain, which processes the signal from your eye? Same. And your conscious mind, which experiences the output of your brain? Here is where the chain must break, because you never experience a superposition. You experience a definite result. Slit A or slit B, never both. Somewhere in this chain between the quantum particle and your conscious experience forces a selection. Something collapses the superposition. Something chooses one outcome from the many. And von Neumann showed, with mathematical rigor, that the equations themselves never do this. There is nothing in the Schrödinger equation that causes collapse. The collapse is not in the mathematics. The collapse is added by hand by physicists, after the fact, to match what they observe. But no one knows why it happens. No one knows where in the chain it happens, and no one knows what causes it. This is the measurement problem, the central unsolved problem in the foundations of quantum mechanics. It has been unsolved since 1926, not because physicists are not smart enough, because the problem is genuinely, fundamentally hard. Every proposed solution leads to a radically different picture of reality. And the answer to the measurement problem is, quite literally, the answer to the question, what is real? Here are the serious proposals, the actual interpretations, as debated by physicists and philosophers of physics today. The Copenhagen interpretation, the oldest and most widely taught, says, do not ask. The wave function is not a physical thing. It is a mathematical tool for calculating probabilities. Before measurement, the particle does not have a definite position, not because we do not know its position, but because the question, what is its position, has no answer. The particle is not somewhere we haven't looked. It is genuinely indeterminate. Measurement does not reveal a pre-existing property. Measurement creates the property. The question, what was the particle doing before we measured it, is meaningless. There is no before measurement story. There is only the measurement and its result. Niels Bohr, the architect of the Copenhagen interpretation, the man who built the conceptual framework that every physics student learns in their first quantum mechanics course, was explicit about this. He did not say that consciousness collapses the wave function. He said something more subtle and more radical. He introduced the principle of complementarity. Some properties of a quantum system, like wave behavior and particle behavior, are mutually exclusive. You can measure one or the other, never both, simultaneously, and neither description is complete on its own. The particle is not really a wave that sometimes looks like a particle. It is not really a particle that sometimes looks like a wave. It is something for which human language has no word, something that reveals different aspects of itself depending on how you ask the question. The answer depends on the question, and there is no question that reveals everything. Bohr did not merely say that we lack information about what happens between measurements. He said the question itself is empty, semantically meaningless, like asking, what is north of the North Pole? The question has the grammatical form of a meaningful question but no referent. There is no, between measurements, reality to inquire about. Reality, at the quantum level, is not a story with a beginning, middle, and end. It is a series of measurement events with nothing connecting them. This is far more radical than your consciousness creates reality. This is, there may be no reality between measurements. The universe is not a movie. It is a series of photographs with no film connecting them. The frames exist. The story between the frames does not. The many worlds interpretation proposed by Hugh Everett III in 1957, dismissed for decades as science fiction, now increasingly popular among theoretical physicists and cosmologists, says, the wave function never collapses. Both outcomes happen. When the particle is measured, the universe does not choose. The universe splits. In one branch, the particle went through slit A, and you see slit A, and your brain records slit A, and your entire reality is the slit A branch. In the other branch, the particle went through slit B, and a different version of you sees slit B, and a different version of your brain records slit B, and a different version of your entire reality is the slit B branch. Both branches are real. Both branches are physical. Both contain conscious beings who believe they are the only version of themselves. You experience only one branch because you are inside it. The other branch is equally real but unreachable, undetectable, permanently severed from your experience by the mathematics of decoherence. Many worlds does not require consciousness. It does not require collapse. It does not require any modification to the Schrödinger equation. It takes the mathematics at face value and accepts where it leads. And where it leads is an infinite number of parallel universes, constantly branching at every quantum event, every radioactive decay, every photon absorption, every molecular interaction, creating an inconceivably vast tree of reality in which every possible outcome of every possible measurement is realized somewhere. The price of eliminating the measurement problem is an infinite multiplication of reality. Whether that price is acceptable is not a question physics can answer. It is a question of metaphysical taste. Objective collapse theories such as the GRW theory, Girardi, Rimini, Weber, and Penrose's gravitational collapse theory say, the collapse is real and physical, but it is not caused by consciousness. It is caused by a physical process that we have not yet fully understood. In the GRW theory, the collapse happens spontaneously, randomly, at a rate that is negligible for a single particle, but overwhelmingly fast for a macroscopic object containing trillions of particles. In Penrose's theory, the collapse is caused by gravity, when a superposition involves a sufficient difference in the gravitational field. Space-time itself becomes unstable and forces a selection. These theories make specific predictions that differ from standard quantum mechanics, and experiments are currently underway to test them. Cubism, quantum Bayesianism, developed by Christopher Fuchs and Rudiger Schack, says something radically different from all of the above. Cubism says that the wave function does not describe the physical state of the world. It describes the state of an agent's beliefs about the world. When I assign a wave function to a particle, I am not describing what the particle is. I am describing what I expect to happen when I measure it. The wave function is my expectation, personal, subjective, belonging to me. Your wave function for the same particle may be different from mine if we have different information, and both are valid. Both are correct, because the wave function is not a portrait of reality. It is a portrait of an agent's relationship with reality. The collapse of the wave function in cubism, is not a physical event in the world. It is an update of my beliefs in light of new evidence, exactly like updating a probability estimate in Bayesian statistics. When I measure a particle and get a result, I do not cause something to happen in the external world. I learn something, and I update my expectations accordingly. There is no measurement problem because there is no collapse to explain. There is only me updating my expectations based on my experience. Cubism is not solipsism. It does not deny the existence of the external world. Fuchs is emphatic about this. The world is real. The world pushes back. When I measure a particle, I am interacting with something genuinely external to me, and the result genuinely surprises me. It is not generated by my mind. But cubism insists that quantum mechanics, as a mathematical formalism, is a theory about agents' interactions with the world, not about the world itself. The wave function is a tool, not a portrait. The map is not the territory, and the question, what is the territory really like, independent of any map, may not have an answer that physics can provide. This is a humility about the limits of physics that most interpretations lack, and it is, in its own way, as radical as many worlds. Now, here is where the common belief about consciousness and quantum mechanics gets something right for entirely the wrong reasons. Eugene Wigner, the Nobel Prize-winning Hungarian-American physicist, one of the founders of quantum field theory, the man who first applied group theory to quantum mechanics, proposed in 1961 that consciousness might indeed play a role in the collapse of the wave function, not in the casual sense of your thoughts create reality, in the precise mathematical sense that the von Neumann chain must terminate somewhere, and the only known entity that experiences definite outcomes, the only known break in the chain of quantum superpositions, is consciousness. Wigner illustrated this with a thought experiment now known as Wigner's friend. Imagine a laboratory. Inside the laboratory, a physicist, Wigner's friend, performs a quantum measurement. She observes a particle and gets a definite result: spin up. For her, the wave function has collapsed. She sees a definite outcome. She writes it in her notebook. From her perspective, the measurement is complete. Reality is determined. But Wigner is outside the laboratory. He has not looked inside. From his perspective, treating the entire laboratory, including his friend, as a quantum system, the Schrödinger equation says that his friend is in a superposition. She is simultaneously in the state saw spin up and wrote spin up in her notebook, and the state saw spin down and wrote spin down in her notebook. From outside, the wave function has not collapsed. From inside, it has. Who is right? If Wigner opens the door and asks his friend what she saw, he will get a definite answer, and his friend will confirm that she saw that answer before he opened the door. She experienced a definite outcome, while Wigner still described her as being in superposition. The two descriptions are contradictory, and quantum mechanics provides no mechanism for resolving the contradiction. The mathematics treats Wigner and his friends symmetrically, but their experiences are not symmetric. His friend experienced a definite outcome. Wigner did not until he looked. In 2019, a team at Heriot-Watt University in Edinburgh actually performed a version of this experiment, not with people, but with entangled photons acting as observer and super-observer. The result confirmed that both descriptions, the friends and Wigner's, are simultaneously valid. Both are correct within their own reference frames. There is no single, objective, observer, independent fact of the matter. The concept of what actually happened depends on who you ask. This is not philosophy. This is experimental physics published in a peer-reviewed journal, and it suggests that the notion of a single, objective reality shared by all observers, independent of observation, may not be a feature of the universe we live in. Wigner's argument was careful. He did not say that consciousness creates reality. He said that the only place where the transition from both outcomes to one outcome is definitively known to occur is at the level of conscious experience. Everything below that particle, detector, eye, brain can in principle exist in superposition. The conscious experience cannot, or at least we have no evidence that it can. Therefore, Wigner argued, consciousness may be the boundary where quantum superposition ends and definite reality begins. This is not the same as your thoughts create reality. Wigner's proposal does not give you the power to choose which outcome occurs. It does not say you can manifest a specific reality by wanting it hard enough. It says that consciousness may be the condition under which the universe commits to a specific outcome, any outcome, rather than remaining in an indefinite superposition. You do not choose the result. You are the occasion for a result to exist. Most physicists today do not accept Wigner's proposal. Decoherence, the process by which quantum superpositions become effectively classical through interaction with the environment, is widely regarded as the explanation for why macroscopic objects do not exhibit quantum behavior, and it does not invoke consciousness at any stage. Here is how decoherence works. A quantum superposition is maintained by a delicate phase relationship between its components, a relationship called coherence. If the superposed system remains isolated from its environment, the coherence is preserved and quantum effects persist. But if the system interacts with its environment, and every macroscopic system interacts with its environment constantly, unavoidably, through photons, air molecules, thermal radiation, the coherence leaks out. The phase relationship between the components of the superposition becomes entangled with the trillions of particles in the environment. The information that distinguishes slit A from slit B does not disappear. It spreads into the air, into the detector, into the walls of the room, into the photons scattering off every surface. It becomes so diluted, so dispersed, so entangled with so many particles, that recovering it becomes practically impossible. Not theoretically impossible, practically impossible. The superposition does not collapse in a fundamental sense. It becomes invisible, drowned in noise, unmeasurable. For a single photon in a vacuum, decoherence takes an extremely long time, effectively forever. For a dust grain floating in air, decoherence takes about 10 to the minus 31 seconds, a trillionth of a billionth of a second. For a human brain, warm, wet, teeming with 100 billion neurons firing electrochemical signals, decoherence is essentially instantaneous. This is why you never experience a superposition. Not because your consciousness collapses it, because the environment collapses it long before the signal reaches your brain, long before any neuron fires, long before any conscious experience arises. The quantum world becomes classical, not because minds observe it, but because the environment overwhelms it. The heat of the room destroys quantum coherence, the way sunlight destroys a shadow. This is powerful. This is convincing. This is the reason most physicists consider the consciousness question irrelevant to quantum mechanics. But, and this is the honest part, the part that the textbooks often gloss over, decoherence does not solve the measurement problem. Decoherence explains why we do not see macroscopic superpositions. It does not explain why we see one specific outcome rather than another. It does not explain the choice. It pushes the mystery back one step from, why does the wave function collapse, to, why do I experience this branch rather than that branch? But it does not eliminate the mystery. The measurement problem remains open. Decoherence has not closed it. Nothing has closed it. In 1978, John Archibald Wheeler, the physicist who named the black hole, who was Niels Bohr's last collaborator, who mentored Richard Feynman, proposed an experiment that made the measurement problem even more disturbing: the delayed choice experiment. In Wheeler's thought experiment, later performed in actual laboratories, most recently with photons bounced off a satellite in Earth orbit, the decision about whether to measure which path a photon takes is made after the photon has already passed through the slits. The experimenter waits until the photon has traversed the apparatus, until it has already either gone through one slit or both slits, until its behavior at the slits is, in any classical sense, already determined, and only then decides whether to insert a which path detector or not. If the detector is inserted, the photon behaves as if it went through one slit. If the detector is not inserted, the photon behaves as if it went through both slits. The photon's behavior in the past is determined by a measurement choice made in the future. This is not a theoretical prediction. This has been experimentally confirmed, repeatedly, with increasing precision and increasing distance. In 2007, a team led by Alan Aspect, who would later win the Nobel Prize for his work on entanglement, performed a delayed choice experiment with single photons. In 2012, a team at the University of Vienna extended it, using entangled photon pairs. In 2017, an Italian-Austrian collaboration bounced photons off a satellite orbiting 3,500 kilometers above the Earth, making the delayed choice after the photon had traveled thousands of kilometers through space. In every case, the result was the same. The photon's past behavior was determined by a future measurement. The delayed choice experiment demonstrates that the photon does not decide to be a wave or a particle when it reaches the slits. It decides, or the universe decides, when it is measured. And if the measurement happens after the photon has already passed the slits, then the decision reaches backward in time. Wheeler called this the participatory universe. Not a universe that exists independently, waiting to be observed. A universe that is, in some deep and not fully understood sense, brought into being by the act of observation. No phenomenon is a phenomenon until it is an observed phenomenon, Wheeler said. He meant this in the ruthlessly precise sense of the experimental evidence. The photon has no definite history, not even a past history, until a measurement is performed. This is stranger than any claim about thoughts creating reality. The common belief says, your thoughts shape the future. Wheeler's experiment suggests that measurement shapes the past. The arrow of causation, in quantum mechanics, does not always point forward. The future can reach back and shape the past. Not in the science fiction sense of time travel, in the precise, experimentally verified sense that a photon's path through an apparatus, its physical trajectory through space, is not determined until after it has already traveled that path. Let me be honest about what we have established so far, because honesty is the only currency worth spending in this territory. What is wrong about the quantum law of being as popularly presented? Your thoughts do not collapse wave functions. Consciousness, in the standard understanding of quantum mechanics, is not required for measurement. Decoherence explains why the classical world appears classical without invoking minds. You cannot manifest a parking space by intending at the quantum level. The gap between quantum effects and macroscopic human decisions is vast, roughly 30 orders of magnitude. A quantum superposition in a single atom lasts for nanoseconds in a warm environment. A human thought takes approximately 300 milliseconds. The decoherence time for a neuron, a single nerve cell, is approximately 10 to the minus 20 seconds. By the time your brain has produced a single thought, the quantum states in your neurons have decohered trillions upon trillions of times. The quantum world and the world of human intention are separated by an abyss of scale that no amount of wishful thinking can bridge. Quantum biology is real but limited. Photosynthesis uses quantum coherence to optimize energy transfer across molecular distances. Bird navigation may involve quantum entanglement in the cryptochrome molecules of the retina. These are genuine quantum effects in biological systems, but they operate at the molecular level, over distances of nanometers, for timescales of femtoseconds. They do not scale up to the level of thoughts, decisions, or intentions. Anyone who tells you that quantum physics proves you create your reality is either confused about the physics or selling you something. Usually both. What is genuinely unsolved? The measurement problem is real and open. No interpretation has achieved consensus. The von Neumann chain has no agreed-upon termination point. Decoherence does not explain why you experience one outcome rather than another. Wheeler's delayed choice experiment is real and confirmed. The photon has no definite history until measured. At least one serious interpretation cubism places the agent at the center of the theory. At least one Nobel laureate Wigner argued that consciousness may be relevant. And the most popular alternative, many worlds, requires an infinite number of parallel universes, which is not obviously more parsimonious than invoking consciousness. The honest position is not consciousness creates reality. The honest position is not consciousness is irrelevant. The honest position is we do not know. The measurement problem is the deepest open question in physics, and the answer, whatever it turns out to be, will reshape our understanding of what it means to exist. In the Gospel of John, the opening verse reads, "In the beginning was the Logos, the Word, the principle of order, the organizing intelligence that precedes and generates the physical world. The universe did not begin with matter, it began with information, with structure, with something that is not physical, but that gives rise to the physical." The early church fathers Origen, Augustine, Maximus the Confessor, understood the Logos not merely as a spoken word, but as the rational principle embedded in the fabric of creation. The Logos is the reason the universe is intelligible, the reason mathematics works, the reason physics is possible, the reason the human mind can comprehend the structure of the cosmos. Without the Logos, there is no order. Without order, there is no physics. Without physics, there is no universe. John Wheeler, no theologian, but a physicist of the deepest intuition, arrived at a strikingly similar conclusion from pure physics. "It from bit," he wrote in 1990. "Every it, every particle, every field of force, even the space-time continuum itself derives its function, its meaning, its very existence entirely from binary choices, bits, yes or no answers. The physical world derives from information, matter derives from measurement, being derives from observation." Wheeler did not cite John's Gospel. He did not need to. The structure announced itself through the mathematics. The Logos precedes the cosmos. Information precedes matter. The word comes before the world. In the Buddhist tradition, the Dhammapada, one of the oldest collections of the Buddha's teachings, opens with, "Mind is the forerunner of all actions. All deeds are led by mind, created by mind." This is not quantum mechanics. The Buddha was not talking about wave function collapse. He was talking about a psychological and phenomenological observation, that the world as you experience it is shaped by the quality of your attention, the structure of your perception, the habits of your mind. You do not create the physical world with your thoughts, but you do create the experienced world, the world of meaning, of suffering, of liberation with the quality of your awareness. But there is a common mistake that must be addressed. Many people collapse the distinction between these two claims. They take the Buddhist insight mind shapes experience and the quantum mystery measurement shapes physics and smash them together into your mind shapes physical reality through quantum mechanics. This is wrong. The two claims operate at different levels. The Buddhist claim is about the phenomenology of experience. The quantum claim is about the formalism of physics. They are not the same claim, and pretending they are does violence to both. But they are not unrelated. They both point to the same structural insight, that the relationship between the observer and the observed is not passive. That observation is not a transparent window onto a pre-existing world. That the act of looking, whether through a photomultiplier tube or through the lens of human attention, participates in the constitution of what is seen. The nature of that participation is radically different in physics and in Buddhism, but the structure is the same, and the structure is worth taking seriously. The measurement problem is not solved. The relationship between consciousness and physics is not understood, and the deepest question in quantum mechanics, what is the observer, is also the deepest question in every contemplative tradition that has ever existed. We do not have the answer, but we have, for the first time in history, a rigorous scientific framework in which the question is not merely philosophical, it is experimental, it is mathematical, it is testable, and the tests are underway. The question of what it means to exist, to be, to observe, to participate in reality is no longer confined to monasteries and philosophy departments. It is being asked in laboratories, in underground detectors, in satellite experiments, in the mathematics of quantum field theory. The question has escaped from religion and philosophy into physics, and physics so far has not been able to answer it. That silence, that open question, that genuine not knowing is more interesting than any premature answer, and it is where we begin. Nothing is solid. This is not a philosophical claim. This is not a spiritual intuition. This is what the most fundamental and most precisely tested theory in the history of physics, quantum field theory, says about the nature of matter. The rock on your desk is not a solid object made of tiny solid particles. Your body is not a collection of atoms that are themselves collections of smaller atoms. At the deepest level, there are no things at all. There are only fields invisible, omnipresent, extending across the entire universe, and the patterns they make when energy disturbs them. Particles are not objects, they are vibrations. Matter is not substance, it is pattern. And the empty space between atoms is not empty. It is the most active, most creative, most restless medium in the known universe. This is quantum field theory, and what it says about the nature of being is more strange and more beautiful than any simplified version has ever captured. To understand what quantum field theory actually says, you need to understand the revolution it represents. Because QFT does not simply update Newtonian physics. It replaces the entire ontology, the entire picture of what the universe is made of. In Newtonian physics, the universe is made of particles. Small, solid, billiard ball-like objects that have definite positions, definite velocities, definite trajectories. They bounce off each other. They attract and repel each other through forces. They are the fundamental stuff of reality. Everything from a grain of sand to a galaxy is made of these particles, arranged in different configurations. The particle is the thing. The thing is real. The thing is fundamental. In quantum mechanics, the first quantum revolution particles became stranger. They could be in superpositions. They could be entangled. They obeyed the uncertainty principle, but they were still, at some level, things. Quantum mechanics describes the behavior of particles, weird particles, particles that do not have definite positions until measured, but still at the conceptual level, things, objects, entities that exist. Quantum field theory abolishes the particle. Not as a useful approximation, particles remain extraordinarily useful for calculations, and physicists talk about particles constantly. But as a fundamental ontological category, as the answer to the question, what is the universe made of, the particle is gone. In QFT, the fundamental entities are not particles. They are fields, continuous, infinite, space-filling mathematical objects, one for each type of particle. There is an electron field that pervades all of space, not concentrated here or there, not localized at specific points, but present everywhere, at every point, like a vast invisible ocean. There is a photon field, the electromagnetic field that pervades all of space. There is a quark field, a gluon field, a Higgs field, a neutrino field. Each field extends across the entire universe, from one edge of the observable cosmos to the other. Each field exists at every point in space and at every moment in time. And what we call particles are not objects sitting in the fields, like boats on an ocean. They are the fields. They are localized excitations, quantized vibrations, patterns of energy concentrated in small regions of the field, propagating through space like waves propagating through water. An electron is not a tiny sphere orbiting an atomic nucleus. An electron is a quantized excitation of the electron field, a specific amount of energy and momentum concentrated in a small region of the field, propagating through space, interacting with other fields. The electron field is the ocean. The electron is the wave. If the wave dissipates, if the electron annihilates with a positron, for example, the electron ceases to exist, but the field remains. The field was there before the electron appeared. The field will be there after the electron vanishes. The field is fundamental. The particle is derivative. The particle is what the field does. The field is what is. This is not an analogy. This is the mathematics of quantum field theory, developed by Paul Dirac in the late 1920s, refined into its modern form by Richard Feynman, Julian Schwinger, and Sein Ichiro Tomonaga in the late 1940s work, for which all three shared the Nobel Prize in 1965. The key insight was renormalization, a mathematical technique for handling the infinities that arise when you calculate how quantum fields interact with each other. The infinities appear because virtual particles, those vacuum fluctuations we will discuss shortly, contribute to every calculation, and their contributions diverge to infinity. Renormalization tames these infinities by absorbing them into the measured values of physical quantities like mass and charge. The technique was initially controversial. Dirac himself called it ugly and doubted its validity. But the predictions it produced were so staggeringly accurate, matching experiment to 12 decimal places in some cases, that the physics community accepted it as the foundation of modern particle physics. Quantum field theory is the framework that underlies the standard model of particle physics, the theory that predicted the existence of the Higgs boson decades before it was found, that explains 3 of the 4 fundamental forces, that has been tested to a precision unmatched by any other theory in any branch of science. When physicists say everything is a field, they are not being poetic. They are describing the mathematical structure of the most accurate theory in the history of science. Now let me tell you about the vacuum. Because the vacuum, the empty space where no particles exist, is the most interesting place in the universe. In classical physics, a vacuum is nothing. Remove all matter, remove all radiation, and what remains is empty space, a blank canvas, a stage with no actors, a container with nothing inside. The vacuum is the absence of everything. In quantum field theory, this is impossible. The vacuum is not empty. It cannot be empty. The reason is the Heisenberg uncertainty principle, the same principle that prevents a particle from having both a definite position and a definite momentum simultaneously. Applied to fields, The uncertainty principle says that a field cannot have both zero amplitude and zero rate of change simultaneously. If the field were perfectly zero everywhere, perfectly still, perfectly empty, then both its amplitude and its rate of change would be exactly determined. The uncertainty principle forbids this. Therefore, the field cannot be perfectly zero. Even in the vacuum, even in the absence of all particles, all radiation, all detectable matter, the quantum fields fluctuate. They jitter. They vibrate. Random, unpredictable, irreducible fluctuations in the energy of the field, popping in and out of existence too quickly to be observed directly, but with real, measurable consequences. These are called vacuum fluctuations, or, more dramatically, virtual particles, pairs of particles, and antiparticles that materialize out of the vacuum, exist for an immeasurably brief moment, governed by the uncertainty principle. The more energy they borrow, the shorter they can exist and annihilate each other before they can be detected directly. An electron and a positron flickering into existence and vanishing, a quark and an antiquark appearing and disappearing, photons materializing from nothing and returning to nothing. The vacuum is not empty. It is a seething foam of virtual particles, constantly creating and destroying themselves, a roiling ocean of potential being flickering in and out of existence at every point in space, at every moment in time. This is not abstract mathematics. Virtual particles have measurable effects on real particles. The Lamb shift, a tiny difference in the energy levels of hydrogen that was measured by Willis Lamb in 1947, is caused by the interaction between the electron in the hydrogen atom and the virtual particles surrounding it. The electron's charge and mass are slightly altered, renormalized, by the cloud of virtual particles that perpetually surrounds it. The electron you measure in a laboratory is not a bare electron. It is a dressed electron, an electron wearing a coat of virtual particles that slightly shifts its properties. The vacuum is not a backdrop. The vacuum participates. The anomalous magnetic moment of the electron, the most precisely measured quantity in all of physics, agrees with the theoretical prediction from quantum electrodynamics to 12 decimal places. 12. This prediction includes the contributions of virtual particles at every level, virtual photons, virtual electron-positron pairs, virtual muons, virtual everything. The theory works because the vacuum is real. The virtual particles are real not as individual detectable entities, but as contributors to measurable physical quantities. The seething vacuum is not a metaphor. It is a mathematical necessity, confirmed to a precision of 1 part in a trillion. Is this real? Or is it just a mathematical artifact, a quirk of the equations that does not correspond to physical reality? It is real. And the proof is an experiment performed in 1948 by Hendrik Casimir, the Casimir effect. Take 2 uncharged metal plates and place them very close together in a vacuum, a few hundred nanometers apart, about 1/1000th the width of a human hair. Between the plates, only certain wavelengths of virtual particles can fit the plates, impose a boundary condition, like the walls of a concert hall restricting which sound frequencies can resonate inside it. Only standing waves whose wavelength divides evenly into the gap can exist between the plates. Outside the plates, all wavelengths are permitted, no boundary, no restriction. The result: there are more virtual particle modes, more possible fluctuations outside the plates than between them. This imbalance creates a net radiation pressure, a real, physical, measurable force pushing the plates together. The vacuum itself squeezes them. The force is small at a separation of 100 nanometers. It amounts to about 1 atmosphere of pressure per square centimeter, which sounds large, but acts over an incredibly tiny area. It was first measured definitively by Steve Lamoureux in 1997, using a torsion pendulum sensitive enough to detect forces of a few piconewtons. The measurement matched Casimir's 1,948 prediction to within 5%. Subsequent experiments have improved the precision to better than 1%. The vacuum pushes the plates together. Empty space exerts a force. Nothing has energy. Nothing has structure. Nothing has consequences. The energy density of the quantum vacuum is, depending on how you calculate it, either enormous or infinite. This is one of the great unsolved problems in physics, the cosmological constant problem, sometimes called the worst prediction in the history of physics. Naive calculations from quantum field theory predict a vacuum energy density that is 120 orders of magnitude larger than what cosmological observations measure 10 to the 120th power. To put this in perspective, if you were off by a factor of 2, that would be a bad prediction. If you were off by a factor of 1,000,000, that would be a catastrophically bad prediction. A factor of 10 to the 120th is not a bad prediction. It is a conceptual failure of the most spectacular kind. And yet the vacuum energy is not zero. Cosmological observations, the accelerating expansion of the universe, first discovered in 1998 by two independent teams studying Type Ia supernovae, indicate that the vacuum does have energy. A tiny, positive, non-zero energy density that accounts for approximately 68% of the total energy content of the universe. This is dark energy, the most abundant form of energy in the cosmos and the most mysterious. It is everywhere. It fills all of space uniformly. And it is causing the expansion of the universe to accelerate galaxies moving apart faster and faster, the universe growing, stretching, thinning, driven by the energy of the vacuum itself. Something is deeply wrong with our understanding of the vacuum, or something is deeply wrong with our understanding of gravity, or some unknown mechanism cancels most of the vacuum energy but leaves a tiny residue, or some combination of all three. The vacuum is not merely interesting. The vacuum is the frontier. The vacuum is where physics breaks down. And the fact that empty space contains enough energy to dominate the evolution of the entire universe should permanently cure anyone of the notion that nothing is simple. Now let me tell you what solidity actually is. Because the claim nothing is solid is correct, but the reason it is correct is far more interesting than most explanations suggest. Pick up a rock. It feels solid, hard, impenetrable. Your hand cannot pass through it. The rock resists. It pushes back. This is what we call solidity, the sensation of matter resisting matter, of one object preventing another from occupying the same space. But the rock is almost entirely empty space. The atoms that compose the rock, silicon, oxygen, aluminum, iron, are themselves almost entirely empty. The nucleus of an atom, the tiny dense core containing protons and neutrons, occupies roughly 1/1,000,000th of the atom's total volume. If an atom were the size of a football stadium, the nucleus would be a marble on the 50-yard line. The stands, the field, the sky above all empty. The entire perceptible structure of the atom is concentrated in a space so small that it defies intuition. The rest, the vast, overwhelming majority, is occupied by the electron cloud, not tiny spheres orbiting the nucleus like miniature planets, but spread out probability distributions, quantum fields, defined not by a position, but by a probability of being found at each point in space. The electron is not somewhere in the atom. The electron is the entire cloud. The cloud is the electron, and the cloud is almost entirely nothing. So why does the rock feel solid? Why can you not push your hand through it? The answer is not that your hand is hitting the atoms in the rock. The atoms are almost entirely empty. your hand is almost entirely empty. Two clouds of almost nothing approaching each other. The reason they cannot pass through each other is the Pauli exclusion principle, the quantum mechanical law that says no two electrons can occupy the same quantum state simultaneously. When the electron clouds of your hand approach the electron clouds of the rock, the electrons resist being pushed into the same states. The resistance is enormous. It increases exponentially as the electrons are forced closer together. This is the force you feel when you push on the rock, not the impact of solid objects. The rebellion of quantum fields against being compressed into identical states. The solidity of the rock is a quantum field effect. The rock is not solid. The rock is a pattern of fields resisting another pattern of fields. And mass? What gives the rock its weight, its inertia, its resistance to being pushed? Most of the mass of ordinary matter does not come from the Higgs field, contrary to the popular simplification that the Higgs boson gives everything mass. The Higgs field, discovered through the detection of the Higgs boson at the Large Hadron Collider in 2012, is a field that pervades all of space with a non-zero value, even in the vacuum. The universe is saturated with the Higgs field the way the ocean floor is saturated with water. Elementary particles interact with this field as they move through it, and this interaction gives them their intrinsic mass. The stronger the interaction, the greater the mass. The top quark interacts strongly and is very heavy. The electron interacts weakly and is very light. The photon does not interact at all and is massless. The mechanism is elegant, experimentally confirmed, and Nobel Prize winning. But here is what the popular account leaves out. The Higgs field gives mass to the elementary particles, quarks, electrons, W and Z bosons. The quarks inside a proton, however, have masses that add up to only about 1% of the proton's total mass. 1%. The other 99% comes from the strong force from the energy of the gluon field binding the quarks together. The gluons themselves are massless, but their energy, their kinetic energy, their binding energy, the energy of the quantum chromodynamic field itself contributes mass through Einstein's equation E equals mc squared. Energy has mass. The energy of the gluon field, trapped inside the proton, gives the proton 99% of its mass. Your body does not weigh what it weighs because of the Higgs field. Your body weighs what it weighs because of the energy of the quantum fields inside your protons and neutrons. You are heavy because of trapped vibrations. You are heavy because of energy that cannot escape. E equals mc squared. Energy equals mass times the speed of light squared. This is the most famous equation in physics, inscribed on t-shirts and coffee mugs and tattoos around the world, and its meaning is almost always misunderstood. It does not merely say that mass can be converted into energy, though it does say that, and Hiroshima proved it. It says something far deeper. Mass is energy. They are not two different things that can be exchanged, like dollars and euros. They are the same thing, measured in different units, the way 1 mile and 1.6 kilometers are the same distance expressed differently. Mass is energy at rest. Energy is mass in motion. The distinction between them is not physical. It is conventional. It is a choice of units. The rock on your desk has mass because the quantum fields inside its protons contain energy. Specifically, the quarks inside each proton, bound together by gluons, the carriers of the strong force, are moving at approximately half the speed of light, constantly, perpetually, even when the proton is at rest. This motion is kinetic energy. The gluon field binding the quarks is potential energy. Together, this energy through E equals mc squared manifests as mass. If you could release that energy, if you could unbind the quarks and let the gluon field dissipate, the mass would vanish and an equivalent amount of energy would be released. This is what happens in nuclear fission and fusion. This is why a nuclear weapon can destroy a city with a sphere of plutonium the size of a grapefruit. The mass of plutonium is not a substance. It is stored energy. The thing is the energy, the stuff is the field. The rock is a pattern of trapped vibrations pretending to be solid. Here is where religion enters. Not as a source of scientific knowledge, religion does not predict the Casimir effect or the gluon field, but as a repository of insights about the nature of being that resonate with startling precision with what quantum field theory has discovered. In the Quran, the act of creation is described with the phrase kun fayakun, be, and it is. God does not build the world from pre-existing material. God speaks, and reality manifests. The command, the information, the divine word precedes the physical existence. There is no raw material that God shapes. There is only the command and its immediate consequence, being. Creation is not construction. Creation is declaration. Existence is called into being from non-existence through an act of divine speech. Quantum field theory describes a universe in which particles are not constructed from smaller parts. They are called into being from the vacuum, from the quantum fields that permeate all of space through the input of energy. An electron does not pre-exist somewhere, waiting to be assembled. The electron field is everywhere. When sufficient energy is concentrated at a point through a collision, a decay, a quantum fluctuation, the field is excited and an electron appears. The electron is not made. The electron is called into being. The field says be, and it is. The parallel with kun fayakun is structural, not causal. The Quran does not describe quantum field theory, but the architecture of creation, existence, called into being from a pre-existing field of potential, through an act of excitation is the same. In Hinduism, the concept of Maya describes the physical world as a kind of illusion, not in the sense that it does not exist, but in the sense that its apparent solidity, permanence, and independence are illusory. The world appears to be made of solid, separate, self-existing objects. But at the deepest level, the level of Brahman, there are no separate objects. There is only one reality, manifesting in different forms, appearing to be many but being one. The multiplicity is the illusion. The unity is the truth. Quantum field theory supports this structure with remarkable precision. There are not 10 to the 80 electrons in the universe, 10 to the 80 separate, independent, individually existing objects. There is one electron field, a single, continuous, universe-spanning field, and every electron in the universe is an excitation of this same field. The electron in your left hand and the electron in a star 10 billion light years away are not two different things. They are two ripples in the same ocean, two vibrations in the same string, two notes played on the same instrument. The multiplicity of electrons is an illusion of distance and perspective. The underlying reality is one field, one entity, one thing, appearing to be many. Maya, in the language of quantum field theory, is not mysticism, it is mathematics. In Buddhism, the doctrine of dependent origination, pratitya samutpada, teaches that nothing exists independently. Every phenomenon arises in dependence on conditions, on causes, on context, on other phenomena. Nothing has self-nature, svabhava. Nothing exists on its own, by its own power, through its own essence. Everything is relational. Everything is contingent. Everything is a process, not a thing. Quantum field theory is the physics of dependent origination. A particle does not exist on its own. An electron is an excitation of the electron field, but the electron field is coupled to the electromagnetic field, which is coupled to the quark fields, which are coupled to the gluon field, which is coupled back to the electron field through virtual processes that involve every other field in the standard model. No field exists independently. No particle exists independently. Every field depends on every other field. Every particle is a temporary configuration of energy in a web of interdependent fields that spans the entire universe. Remove one field, remove the electromagnetic field, or the Higgs field, or the strong force, and the others change. The electron changes, the proton changes, the atom changes. Nothing is independent. Nothing has self-nature. Everything arises in dependence on conditions. Pratitya samutpada, in the mathematics of gauge symmetry and quantum field interactions. In Christian theology, the doctrine of creatio continua, continuous creation, teaches that God does not merely create the universe at the beginning and then step back. God sustains the universe at every moment. Every instant of existence is a fresh act of divine creation. If God ceased to sustain the world even for an instant, the world would cease to exist. Being is not a gift given once. Being is a gift given continuously, at every moment, at every point in space. The universe does not have its own independent existence. It exists because it is being held in existence. The quantum vacuum mirrors this structure. The fields do not exist on their own, in some self-sustaining, self-perpetuating way. They are sustained by the mathematical structure of the theory, by the symmetries, the conservation laws, the coupling constants that dictate how fields interact. Change a coupling constant. Change the strength of the electromagnetic force by 1%, and the entire edifice of matter collapses. Atoms become unstable. Chemistry becomes impossible. The universe as we know it ceases to exist. The physical world is not self-sustaining. It depends, at every moment, on the precise values of a handful of fundamental constants. Constants that are not explained by any known theory. Constants that appear to be simply given, simply there, holding the universe in existence, the way creatio continua holds the world in being. Thomas Aquinas, the great medieval theologian, distinguished between essence and existence. A thing's essence is what it is, its definition, its nature, its form. A thing's existence is that it is the brute fact that it actually exists rather than merely being possible. For Aquinas, the distinction between essence and existence is the deepest distinction in metaphysics. And only in God are essence and existence identical. Only in God is what it is, the same as that it is. Everything else, every created thing, has an essence that is distinct from its existence. It could have not existed. Its existence is not guaranteed by its nature. Its existence is a gift received from outside, sustained from outside, dependent on something beyond itself. Quantum field theory formalizes this distinction with extraordinary precision. The electron field has a mathematical structure, an essence defined by the Lagrangian of quantum electrodynamics. This essence specifies everything about the electron's properties, its charge, its spin, its interactions. But the essence does not require the field to be excited. The field can exist in its ground state, the vacuum state, with no electrons present. The essence exists without existence. The form exists without the thing. For an electron to actually exist, for the field to be excited, for the vibration to occur, energy must be added. Something must act on the field from outside. The electron's existence is not contained in its essence. Its existence is a gift of energy, a contingent, unnecessary, bestowed actuality that the essence alone does not guarantee, Aquinas' distinction between essence and existence, written in the 13th century, maps onto the distinction between the quantum field and its excitations, with a precision that neither the theologian nor the physicist could have anticipated. Nothing is solid. This is correct, but the reason is precise and specific. Nothing is solid, because solidity is a macroscopic phenomenon generated by quantum field effects. The Pauli exclusion principle, the electromagnetic force, the energy of the gluon field, the rock is not a thing. It is a pattern, a temporary, localized, energy-dependent pattern in fields that span the universe. Nothing is empty. This is also correct, but not in the way meditation instructors claim. Nothing is empty because the quantum vacuum is not empty. It seethes with virtual particles, exerts measurable forces, contains energy that we cannot fully calculate, and may be the source of the dark energy that is accelerating the expansion of the universe. Everything is vibration. This is correct too in the precise sense that every particle is a quantized vibration of a quantum field, not a metaphorical vibration, not an energy frequency that you can raise by thinking positive thoughts. A literal, mathematical, experimentally verified vibration of a quantum field that pervades all of space. The simplified versions of these claims miss the depth, but the structure is correct. The universe is not made of things, it is made of patterns, of processes, of vibrations in fields, of being that is not static, not permanent, not independent, but dynamic, contingent, and relational. Every religion we have examined has said the same. Reality is not what it appears. The solid is not solid, the empty is not empty, the separate is not separate, and the being of things is not their own. The fields vibrate, the particles appear, the vacuum seethes, and the question of why any of it exists at all, why there is something rather than nothing, why the fields have the values they have, why the vacuum has the energy it has, remains the deepest unanswered question in science and in theology and in philosophy, and in the quiet moments when you hold a rock in your hand and wonder what exactly you are holding. In 1935, Albert Einstein published a paper that he believed would expose quantum mechanics as incomplete. The paper, co-authored with Boris Podolsky and Nathan Rosen, described a thought experiment so strange, so apparently absurd, that Einstein was convinced it proved quantum mechanics could not be the final theory of reality. The paper is known by the initials of its authors EPR, and it introduced a phenomenon that Einstein dismissed as spooky action at a distance. The phenomenon was quantum entanglement, and Einstein was right that it was spooky. He was wrong that it proved quantum mechanics incomplete. In fact, entanglement turned out to be one of the most profound discoveries in the history of physics, a discovery that demonstrates, with mathematical rigor and experimental certainty, that the universe is not made of separate parts, that the notion of isolated, independent objects that have their own properties, their own identities, their own existence, regardless of what is happening elsewhere, is wrong. Not approximately wrong. Not wrong in some subtle philosophical sense. Experimentally, demonstrably, Nobel Prize-winningly wrong. Here is what entanglement is. Here is what it is not. And here is why it matters more than almost anything else in physics for the question of what it means to exist. Start with two particles. Create them in a way that links their quantum states, for example, by producing two photons from a single source, such that their polarizations are correlated. If one photon is vertically polarized, the other is horizontally polarized, and vice versa. But, and this is the critical point before measurement, neither photon has a definite polarization. In the Copenhagen interpretation, the question, what is this photon's polarization, has no answer until you measure it. The photon is in a superposition, a quantum state that encompasses both possibilities simultaneously, with no definite value. Now separate the two photons, send them to opposite ends of a laboratory, or opposite ends of a city, or opposite ends of the Earth, or opposite ends of the universe, it does not matter. The entanglement persists regardless of distance. The two photons are described by a single quantum state, a single wave function that cannot be decomposed into two independent wave functions. They are not two things. They are one thing, expressed in two locations. Measure the polarization of photon A. You get a result, say, vertical, instantly, not at the speed of light, not after some delay, but simultaneously with your measurement photon, B's polarization becomes determined. It is horizontal. Not was always horizontal and you just didn't know. Becomes horizontal. At the moment of your measurement of photon A, photon B's quantum state changes regardless of the distance between them, regardless of whether any signal could have traveled from A to B, regardless of whether B is in the next room or in the Andromeda galaxy. The correlation is instantaneous. Einstein found this unacceptable. It violated everything he believed about the nature of physical reality. Einstein was not merely a great physicist. He was a philosopher of physics, a thinker who cared deeply about what the equations meant, not just what they predicted. And what Einstein believed, with the conviction of a lifetime spent building the most successful theories in history, was that physical reality is local and realistic. Local means that physical influences propagate at or below the speed of light. Nothing here can instantaneously affect something there. Realistic means that physical properties exist independently of measurement. The moon is there whether you look at it or not. These two principles, locality and realism, were, for Einstein, the bedrock of rational physics. Without them, science itself became incoherent. Without locality, causation dissolves. Without realism, there is nothing to discover. Physics becomes a game of predictions with no underlying reality to predict about. If photon B's polarization is determined by a measurement performed on photon A, and if A and B are separated by a distance that light cannot cross in the time between the measurement and the determination, then either A, some influence traveled faster than light, violating special relativity and locality, or B, the photons had definite polarizations all along, determined at the moment of creation, and the measurement simply revealed a pre-existing fact like opening a sealed envelope. Einstein preferred option B. The photons, he argued, must carry hidden variables, predetermined values that quantum mechanics, in its current formulation, simply fails to describe. Quantum mechanics is incomplete. It gives correct predictions but misses the deeper reality. The spookiness is an artifact of our ignorance, not a feature of the universe. This was the EPR argument, published in the Physical Review in May 1935. It was elegant, intuitive, and philosophically powerful. It was also, as John Bell would demonstrate 29 years later, experimentally testable and wrong. In 1964, the Northern Irish physicist John Stuart Bell, a quiet, meticulous theorist working at CERN, the European Organization for Nuclear Research in Geneva, proved that Einstein was wrong. Not by philosophical argument, not by appeal to authority, not by invoking the Copenhagen interpretation or any other interpretive framework, by mathematics, pure, clean, interpretation, independent mathematics that any physicist could verify. Bell's argument was devastatingly simple. He asked, if Einstein is right, if the particles carry hidden variables, If their properties are predetermined at the moment of creation, what are the maximum correlations you could observe in an experiment? He derived an inequality now called Bell's inequality that places a strict, absolute, mathematical upper limit on the strength of correlations between entangled particles if hidden variables exist. The inequality is not approximate. It is not usually satisfied. It is always satisfied, without exception, by any theory in which particles have definite properties and influences travel no faster than light. If Einstein is right, if local realism is true, then the correlations measured in any entanglement experiment must satisfy Bell's inequality. They must be below a certain threshold. The mathematics is unambiguous and airtight. Bell then calculated what quantum mechanics predicts for the same correlations, and the quantum prediction was different. Quantum mechanics predicts correlations that violate the inequality, that exceed the threshold, that are stronger than any local realistic theory, any theory, with hidden variables and no faster than light influences can possibly produce. The excess is not small. It is large, measurable, and unambiguous. If quantum mechanics is correct, Bell's inequality is violated. If local realism is correct, Bell's inequality is satisfied. The two predictions are different. The two predictions are testable, and the test determines which picture of reality is true. Bell published his result in a relatively obscure journal, Physics Physique Physica, and for several years almost no one noticed. The physics community was focused on other things: quarks, the Standard Model, high-energy particle physics. A theorem about the foundations of quantum mechanics seemed, to most physicists, like philosophy. Not their concern, but a handful of experimentalists, most notably John Clauser, recognized that Bell had done something unprecedented. He had taken a question that had been debated for 30 years by Einstein, Bohr, and their intellectual heirs, a question that everyone assumed was purely philosophical, and turned it into an experiment, a question that could be answered by building an apparatus and counting photons. The experiments began in the 1970s. John Clauser, an American physicist who had read Bell's paper and recognized its revolutionary implications when most of the physics community had not built the first experimental test of Bell's inequality in 1972, using entangled photons from a calcium cascade source. His results violated Bell's inequality. Quantum mechanics was right, local realism was wrong. But Clauser's experiment had loopholes, technical imperfections that, in principle, allowed a hidden variable advocate to argue that the results were not definitive. The measurement settings were fixed in advance, which meant that, in principle, the photons could have known what was going to be measured and adjusted their behavior accordingly. This is called the locality loophole, the possibility that some subliminal signal passed between the particles before the measurement was completed. In 1982, Alain Aspect, a young French physicist at the University of Paris-Sud, who had spent years preparing for this single experiment, closed the locality loophole. He designed an experiment in which the measurement settings were changed while the photons were in flight after they had been emitted from the source but before they reached the detectors. The settings were switched by high-speed acousto-optical modulators on a timescale of 10 nanoseconds, far faster than any light signal could travel between the two detectors, which were separated by 12 meters. If the photons were communicating with each other, if some subliminal signal were coordinating their responses, it would have to travel faster than light to arrive in time. And yet the correlations still violated Bell's inequality, decisively, unambiguously. The quantum prediction held. Local realism took another blow. Aspect's experiment made the front page of newspapers. It transformed the discussion about Bell's theorem from a niche philosophical debate into a central topic in physics. And it launched a 40-year experimental campaign to close every conceivable loophole, every possible escape route for local realism. In the following decades, experimenters systematically closed every known loophole. The detection loophole, the possibility that the detectors were selectively capturing only the photons that happened to violate the inequality, was closed by experiments using high-efficiency detectors. The freedom of choice loophole, the possibility that the measurement settings were somehow correlated with the hidden variables, was addressed by experiments that derived their measurement settings from distant astronomical events. In 2018, the Big Bell test used the random keystrokes of over 100,000 human volunteers around the world to set the measurement parameters, eliminating the possibility that any physical mechanism could have predetermined the settings. Every experiment, without exception, violates Bell's inequality. Every experiment confirms the quantum prediction. Every experiment refutes local realism. The universe does not contain hidden variables. The photons do not carry predetermined values. The correlations are real, instantaneous, and not explained by any local mechanism. In 2022, Clauser, Aspect, and Anton Zeilinger, an Austrian physicist who extended entanglement experiments to record-breaking distances and pioneered quantum teleportation, shared the Nobel Prize in Physics for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. Local realism is dead, and what replaces it is something that no one fully understands. Here is what entanglement does not mean. It does not mean that you can send signals faster than light. The correlations between entangled particles are real and instantaneous, but they cannot be used to transmit information. When you measure photon A and get vertical, you know instantly that photon B is horizontal, but the person holding photon B does not know what you measured. They see their photon as horizontal but have no way of knowing whether your photon was vertical or whether you measured it at all. The correlation is only visible when both sets of measurements are compared, which requires classical communication, which travels at or below the speed of light. Entanglement creates correlation without communication, connection without signaling, unity without interaction. Here is what entanglement does mean. The universe is not locally real. Locally real means objects have definite properties that exist independently of observation, realism, and influences between objects propagate no faster than light, locality. Bell's theorem and the experiments that confirm it demonstrate that at least one of these assumptions is false. Either objects do not have definite properties independent of observation, which is the Copenhagen view, or influences propagate instantaneously, which is the Bohmian mechanics view, or both, which is the relational quantum mechanics view, or the question is meaningless, which is the cubism view. But what is not possible is for both locality and realism to be true simultaneously. The universe we live in is not the universe Einstein hoped for, and entanglement can do something that sounds like science fiction: quantum teleportation. In 1993, Charles Bennett and colleagues proposed the complete transfer of a particle's quantum state from one location to another, using entanglement and classical communication, without the quantum state ever traversing the intervening space. The state vanishes here and appears there. It does not travel between. Anton Zeilinger's team performed the first experimental teleportation in 1997, and in 2017, the Chinese satellite Micius teleported quantum states from Tibet to orbit, 1,400 kilometers, the longest distance quantum teleportation ever achieved. The state vanished from the ground and appeared in space. It was not broadcast as a signal. It was teleported through the entangled channel. The information was never between. It was here, then there. Entanglement served as the bridge. The implications of entanglement for the nature of being are profound. Because entanglement is not rare, it is not limited to specially prepared laboratory photons. Entanglement is ubiquitous. Every interaction between two quantum systems creates entanglement. Every photon that bounces off an atom becomes entangled with that atom. Every molecule that collides with another molecule becomes entangled. The air in the room around you is a web of entanglement, trillions of molecules interacting with each other every second, creating an ever-expanding network of quantum correlations. Your body is entangled with the chair you sit on, which is entangled with the floor, which is entangled with the earth, which is entangled with the photons from the sun, which are entangled with the nuclear reactions in the solar core. The universe is not a collection of separate objects that occasionally interact. The universe is a single, entangled quantum state, an unimaginably complex web of correlations connecting everything to everything else. This is not mysticism. This is the mathematical consequence of quantum mechanics, applied consistently. The reason we do not experience this entanglement directly is decoherence, the process by which quantum superpositions become effectively classical through interaction with the environment. The entanglement between macroscopic objects is real, but it is scrambled so quickly and so thoroughly by the environment that it becomes practically undetectable. The quantum correlations between your body and the chair are there. They exist in the mathematics, but they are drowned in the thermal noise of 10 to the 26th molecules jostling each other at room temperature. The unity is real. The experience of separateness is the illusion. But the illusion is extraordinarily robust. In 2013, Juan Maldacena and Leonard Susskind, two of the most influential theoretical physicists alive, proposed a conjecture that, if true, would make the connection between entanglement and the structure of space-time itself explicit. The conjecture is called ER equals EPR. ER refers to Einstein-Rosen bridges, wormholes, theoretical tunnels, connecting distant points in space-time, first described by Einstein and Rosen in 1935. EPR refers to the Einstein-Podolsky-Rosen entanglement we have been discussing, also first described in 1935. 2 papers, same authors, same year, one about connections in space-time, one about connections between particles. For 78 years they were treated as completely unrelated phenomena. Maldacena and Susskind proposed that they are the same phenomenon. Every pair of entangled particles, they argued, is connected by a microscopic wormhole, a quantum Einstein-Rosen bridge. The entanglement is the wormhole. The quantum correlation is the geometric connection. The two particles do not influence each other across space. They are connected through space through a tunnel in the geometry of space-time itself that makes distant particles effectively adjacent. Separation, in this picture, is a property of the macroscopic space-time geometry. At the quantum level, there is no separation. Entangled particles are next to each other, connected by a wormhole too small to transmit signals but real enough to maintain correlations. This conjecture builds on an earlier insight, the holographic principle, developed by Gerard Hooft and Leonard Susskind in the 1990s. The holographic principle states that the information content of a volume of space is encoded not in the volume itself but on its boundary, like a hologram, where a two-dimensional surface contains all the information needed to reconstruct a three-dimensional image. The amount of information that can be stored in a region of space is proportional not to the volume of the region but to the area of its surface. This suggests, though, does not prove that the three-dimensional universe we experience may be a projection of a two-dimensional reality at a distant boundary. That the depth of space, the third dimension, the sense that you can walk into the distance, may be an emergent property generated by quantum information on a lower dimensional surface. If ER equals EPR is correct, and if the holographic principle accurately describes the deep structure of the universe, then space itself, the distance between objects, the separation between here and there, the three-dimensional stage on which the drama of physics plays out, may be constructed from entanglement. Space is not the stage on which quantum mechanics plays out. Space is what quantum mechanics creates. Entanglement weaves the fabric of space-time. Separation is not a fundamental feature of reality. Separation is an emergent property of a deeper, undivided quantum state. Mark van Ramsdonk, a theoretical physicist at the University of British Columbia, demonstrated this explicitly in a 2010 paper, showing that if you remove all entanglement from a quantum system, the corresponding space-time geometry falls apart. Literally falls apart. The space-time disconnects into separate, unlinked pieces. Entanglement is the glue. Without it, space dissolves. Every major religion teaches that separation is an illusion, that the apparent multiplicity of the world, the billions of separate objects, separate people, separate beings, conceals an underlying unity. And the parallel with entanglement is not superficial, it is structural. In the Buddhist tradition, the metaphor of Indra's net found in the Avatamsaka Sutra, one of the most philosophically sophisticated texts in Mahayana Buddhism, a text so vast that Chinese tradition says only dragons and nagas can comprehend it in full, describes reality as an infinite net, stretching in all directions, with a luminous jewel at every node. Each jewel reflects every other jewel in the net, and each reflection itself contains reflections of all the other jewels, which contain reflections of all the other reflections, ad infinitum. The net has no center, no edge, no hierarchy. Every point contains every other point. Every part contains the whole. The separation between the jewels is apparent. They look separate. They seem to occupy different positions. They appear to be individual objects, but the reflections make them one. Each jewel is, in its reflections, every other jewel. The individuality is surface. The interconnection is depth. The Huayan school of Chinese Buddhism, which takes the Avatamsaka Sutra as its foundational text, developed this metaphor into a rigorous philosophical system. Fazang, the third patriarch of Huayan, demonstrated Indra's net to the Empress Wu Zetian by placing a Buddha statue in a room lined with mirrors on all sides, walls, ceiling, floor. Each mirror reflected the Buddha. Each mirror also reflected every other mirror's reflection of the Buddha, an infinite recursion of reflections, each containing all the others. This is the nature of reality. Fazang told the Empress, every Dharma, every phenomenon contains every other Dharma. Nothing exists in isolation. Everything interpenetrates everything. Entanglement is Indra's net made physical. Every particle that has ever interacted with another particle is correlated with it, reflects it, in the language of quantum mechanics. The photon from a distant quasar, after 14 billion years of travel, arrives at your retina and becomes entangled with the electrons in your photoreceptors. You now contain, in the quantum correlations of your atoms, information about a quasar 14 billion light-years away. And that quasar is entangled with other systems, which are entangled with others, in an ever-expanding web of correlations that, traced back far enough, connects everything to the initial quantum state of the universe itself. Your body is a jewel in Indra's net. Every jewel reflects every other. The net is the entangled quantum state of the universe. For Zhang's Hall of Mirrors is the Hilbert space of quantum mechanics. In Islam, the concept of Tawheed, the absolute oneness of God, extends beyond theology into ontology. The Sufi philosopher Ibn Arabi developed the concept of Wahdat al-Wujud, the unity of being. There is only one existence, God's existence. Everything that appears to exist, every person, every creature, every atom, every star, is a manifestation tayali of the one divine reality. The apparent multiplicity of the world is real at the level of manifestation, but illusory at the level of essence. There is only one being, appearing as many. The entangled quantum state of the universe is, in a precise physical sense, one thing. Not many things correlated. One thing, a single, global, indivisible quantum state, from which all apparent separations emerge through decoherence. The photon in your laboratory and the photon in Andromeda are not two separate systems that happen to be correlated. They are two aspects of a single quantum state, the state of the universe that cannot be factored into independent parts. Wahdat al-Wujud. In the language of Hilbert space, there is one state. There is one being. The multiplicity is manifestation. The unity is reality. In Christianity, the Apostle Paul describes the community of believers as one body in Christ, a single organism with many members, each different, each necessary, none independent. If one member suffers, all suffer together. If one member is honored, all rejoice together. The body metaphor is not merely organizational, it is ontological. Paul is not saying that believers should act as if they are one body. He is saying they are one body. The unity is real. The separation into individual members is a feature of the surface. The body is the depth. The mystical tradition extends this further. Meister Eckhart, the 14th century Dominican mystic whose sermons pushed the boundaries of Christian orthodoxy, taught that the distinction between the soul and God is, at the deepest level, no distinction at all. The eye with which I see God is the same eye with which God sees me. My eye and God's eye are one eye, one seeing, one knowing, one love. The ground of the soul, Seelengrund, and the ground of God, Gottsgrund, are the same ground, not similar, not analogous, identical. The apparent separation between creature and creator, between self and divine, between here and God, is the surface experience of a unified reality. Gregory of Nyssa, one of the Cappadocian Fathers, among the most sophisticated theologians of the early church, developed the concept of epectasis, the soul's eternal movement toward God, always approaching, never arriving, because God is infinite. The soul and God are never fully separated. The soul's very existence is sustained by divine presence, but the soul also never fully coincides with God, because the infinite cannot be contained by the finite. The relationship is not static unity but dynamic participation, a perpetual entanglement between the finite and the infinite, the creature and the creator, in which neither is independent but neither is identical. Entanglement does not prove that you are God. Entanglement does not prove that all is one in the mystical sense. But entanglement demonstrates that the physical universe is not a collection of separate objects. It is a single entangled state. The separateness you experience, the feeling that you are here and the table is there and the star is far away, is a feature of your experience, not a feature of the quantum state. In the mathematics, there is no separation. In the mathematics, everything is connected. In the mathematics, the universe is one. In Hinduism, the Chandogya Upanishad contains the teaching of Uddalaka to his son Shvetaketu, one of the foundational texts of Advaita Vedanta. Udalaka describes how the one Brahman becomes the many through differentiation, just as clay becomes many pots, gold becomes many ornaments, iron becomes many tools. The pots are different in form. The clay is one. The ornaments are different in shape. The gold is one. The appearances are many. The substance is one. Tat tvam asi, that thou art. The ultimate reality that underlies the universe is the same reality that underlies you. Not similar, not analogous, the same. One substance, appearing as many. The quantum field is the clay. The particles are the pots. The electron field is one spanning the entire universe. The electrons are many, 10 to the 80, in the observable universe. But the many are excitations of the one. Patterns in a single field, forms in a single substance. The pots are different. The clay is one. The electrons are different. The field is one. Tat tvam asi, the electron in your brain and the electron in a supernova are the same field, the same substance, the same being, appearing in different locations, with different energies, in different contexts, but the same. The honest assessment. Entanglement is real. Non-locality is confirmed. Bell's inequality is violated by every experiment ever performed. The universe is not locally real. These are experimental facts, not interpretations. They do not depend on whether you prefer Copenhagen or many worlds or cubism. They are true in every interpretation. The universe we live in does not satisfy local realism, but the religious conclusion that all is one, in the mystical sense, does not follow from the physics alone. Entanglement creates correlations, not consciousness. Non-locality connects quantum states, not souls. The unity of the quantum state is mathematical, not experiential. The fact that your atoms are entangled with distant stars does not mean you are one with those stars in any way that affects your daily experience, your sense of self, or your capacity for compassion. Decoherence ensures that the quantum unity is invisible at the macroscopic level. You experience separateness because, at the level of macroscopic physics, separateness is an extraordinarily good approximation. The quantum unity is real but hidden like the neutrinos of our earlier series, passing through everything without a trace. The structural parallel, however, is undeniable, and it is worth being precise about what we mean by structural parallel. We mean this. The religions say separation is illusion, unity is reality. Physics says separateness is emergent, entanglement is fundamental. The religions say the many arise from the one. Physics says the many particles arise from one field, one quantum state. The religions say every part contains the whole. Physics says every entangled subsystem contains information about every other. The languages are different. The mathematics differs from the poetry. The Hilbert space differs from the meditation hall. But the architecture, the relationship between the one and the many, between the fundamental and the emergent, between the hidden unity and the apparent separation is the same. And the fact that this architecture was discovered independently by contemplatives sitting in silence 2,000 years ago and by physicists counting photons in laboratories is not proof of anything. But it is worth taking seriously. Not as evidence that the mystics were doing physics, not as evidence that the physicists are doing mysticism, but as evidence that reality may have a structure that is deep enough, consistent enough, and universal enough to be glimpsed from multiple directions, through mathematics, through meditation, through prayer, through experiment, different maps, same territory. The question of what that territory ultimately is, whether it is merely mathematical or also spiritual, whether it is merely structural or also conscious, whether it is merely physical or also divine remains open. It is the question we carry into the final part. Particles are not things, they are excitations of quantum fields. The vacuum is not empty, it seethes with zero-point energy. Mass is not intrinsic, it is acquired through interaction with the Higgs field. Separation is not fundamental entanglement, weaves the universe into a single quantum state. And the measurement problem, the question of what forces quantum possibilities into definite outcomes, remains the deepest unsolved problem in physics. So what does all of this mean? Not for physics, we know what it means for physics, but for the question that burns beneath all the equations: what does it mean to exist? What is being? What is this? There is no quantum law of being. Quantum mechanics has no law by that name. No textbook contains it. No physicist uses it. No equation describes it. But the question behind the phrase is legitimate. What does quantum physics reveal about the nature of existence? About the relationship between observer and observed? About the architecture of reality itself? This is the real question. And it has real answers, not definitive answers, but serious proposals from serious physicists, proposals that are stranger and more profound than any simplified version has ever captured. John Archibald Wheeler was the last surviving collaborator of both Niels Bohr and Albert Einstein. He named the black hole. He coined the term wormhole. He developed the Wheeler-DeWitt equation, the most important equation in quantum gravity. He was, by any measure, one of the most creative and visionary physicists of the 20th century. And in the last decades of his life, he became convinced of something extraordinary: that the universe is not made of matter, it is made of information. It from bit, Wheeler wrote in 1990. Otherwise put, every particle, every field of force, even the space-time continuum itself derives its function, its meaning, its very existence entirely, even if in some contexts, indirectly, from the apparatus elicited answers to yes or no questions, binary choices, bits. It from bit symbolizes the idea that every item of the physical world has at bottom, at a very deep bottom, in most instances an immaterial source and explanation. Read that again. Every item of the physical world has an immaterial source. Wheeler was not a mystic. He was not a theologian. He was a physicist, and he arrived at this conclusion through decades of grappling with the measurement problem, the black hole information paradox, and the foundations of quantum mechanics. His reasoning was technical, rooted in the structure of the equations, but his conclusion was stunning. The physical world is made of information. Matter is secondary. Information is primary. The bit precedes the it. Wheeler went further. He proposed the concept of the participatory universe, a universe that does not exist in a fully definite state until it is observed. Not observed by human consciousness. Specifically, Wheeler was careful about this, but observed in the sense of measured, registered, recorded. A universe in which the observer is not a passive spectator but an active participant in the creation of reality. Wheeler illustrated this with a thought experiment called the delayed choice experiment. In the delayed choice experiment, the decision to observe which slit a photon passes through can be made after the photon has already passed through the barrier, and the photon's behavior changes retroactively as if the future measurement reached backward in time and determined the past behavior of the particle. Wheeler interpreted this as evidence that the observer participates in defining the history of the universe, not just the present state, but the past. We are participants, Wheeler wrote, in bringing into being not only the near and the here, but the far away and long ago. The observer does not create reality out of nothing, but the observer participates in the selection of reality from the space of possibilities. The universe is not a machine that runs independently of observation. The universe is a collaborative project between physics and observation, between the possible and the measured, between the wave function and the collapse. Wheeler illustrated this with one of the most astonishing thought experiments in the history of physics, the cosmic delayed choice experiment. Imagine a quasar, a luminous object billions of light years away. Between you and the quasar lies a galaxy whose gravity bends light, creating two paths around it. A photon from the quasar can take path A around the left side of the galaxy, or path B around the right side. If you place a detector that determines which path the photon took, you get particle behavior. The photon took one path or the other. If you place a detector that combines both paths, you get interference. The photon took both paths simultaneously. Here is the astonishing part. The photon left the quasar billions of years ago. It has been traveling through space since before the Earth existed. And your choice of detector made today, in your laboratory, determines whether the photon took one path or two paths billions of years ago. The future measurement reaches backward across cosmic time and determines the past behavior of the photon. The photon has no definite history until you measure it. And no definite history does not mean we don't know which path it took. It means there was no fact of the matter, no path, no history, until the measurement, until the observation, until the participation. Wheeler was not claiming that human consciousness rewrites cosmic history. He was claiming something more precise and more unsettling, that the quantum state of the universe, the full description of physical reality, does not contain definite histories. It contains possibilities, superpositions, and measurements select from among those possibilities, creating definite facts where none existed before. The observer participates in the constitution of the past, not by imagining it, not by intending it, by measuring it, by interacting with it, by asking the question that forces the universe to answer. Wheeler was describing something far more austere and far more strange than any simplified version of "you create your reality." A universe that exists in a state of quantum indeterminacy, a superposition of all possible histories, until an act of measurement selects one history from the many. The selected history then becomes the past, as real and definite as if it had always been determined. But it was not always determined. It was selected by measurement, by interaction, by the participation of an observer in the unfolding of the cosmos. Is consciousness the relevant kind of observer, or is any physical interaction sufficient? This is the question that divides physicists and philosophers, and there are serious proposals on both sides. Roger Penrose, the Nobel Prize-winning mathematician and physicist, co-discoverer of the Penrose-Hawking singularity theorems, inventor of Penrose tiling, author of The Emperor's New Mind, has argued that consciousness is not a computation, that it cannot be replicated by a Turing machine, that it involves a specific physical process. The gravitational self-collapse of quantum superpositions in microtubules, protein structures inside neurons, that are small enough to maintain quantum coherence for biologically relevant timescales. Penrose's collaborator, the anesthesiologist Stuart Hameroff, identified the microtubules as the physical substrate. The theory known as orchestrated objective reduction, or OR, proposes that quantum superpositions in tubulin proteins within microtubules undergo objective collapse, Penrose's gravitational collapse mechanism, at a rate determined by the energy difference between the superposed states. Each collapse event is a moment of conscious experience, a quantum of consciousness. The microtubules, by virtue of their quantum properties, connect the brain to the fundamental level of space-time geometry. Consciousness, in this theory, is not an emergent property of complex computation. It is a fundamental feature of quantum gravity woven into the fabric of the universe at the deepest level. OR is controversial. Many neuroscientists dismiss it on the grounds that the brain is too warm and wet for quantum coherence to survive. Decoherence should destroy any quantum effects in neurons within femtoseconds, far too fast to influence neural computation. But recent experiments have complicated this dismissal. Quantum coherence has been observed in photosynthetic complexes at room temperature. Quantum effects have been implicated in bird navigation. And Hameroff has pointed to experiments suggesting that anesthetics which eliminate consciousness work by disrupting quantum processes in microtubules, not by disrupting classical neural computation. The evidence is not definitive, but it is not negligible, and Penrose is not a crank. He is a Nobel laureate, and his argument from Gödel's incompleteness theorems that mathematical understanding transcends formal computation remains one of the deepest arguments in the philosophy of mind. Giulio Tononi, the neuroscientist at the University of Wisconsin-Madison, has approached consciousness from an entirely different direction with his integrated information theory, IIT. Tononi begins not with physics but with the phenomenology of experience with what consciousness is like. He identifies 5 axioms that any conscious experience must satisfy. It exists, it is real, it is structured, it has shape, it is specific, it is this particular experience, not another, it is unified, it cannot be divided without losing something, and it is definite, it has a particular boundary. From these axioms, he derives a mathematical quantity called phi, integrated information, which measures the degree to which a system generates information that is both differentiated and integrated. The higher the phi, the more conscious the system. IIT makes a radical claim. Consciousness is not something brains do. Consciousness is something that any system with sufficiently high phi possesses. A brain has high phi because its neurons are massively interconnected. Each of the 86 billion neurons in the human brain connects to approximately 10,000 others, creating a web of integrated information that is, as far as we know, the most complex structure in the observable universe. A thermostat has low phi because its components are not integrated. A computer running a simulation of a brain may have low phi, even though it produces the same outputs, because the integrated information depends on the intrinsic causal structure of the system, not on its input-output behavior. A perfect simulation of consciousness is not conscious, any more than a perfect simulation of a hurricane is wet. And here is the radical part. Phi can, in principle, be calculated for any physical system, including quantum fields, including the vacuum, including the universe as a whole. If phi is the measure of consciousness, and if the universe has high phi, which it plausibly does, given that quantum entanglement creates precisely the kind of integrated, non-decomposable information structure that IIT identifies as the substrate of consciousness, then the universe itself possesses some form of experience. Not human experience, not thought, not feeling in the way you feel pain or joy, but something, some minimal experiential quality, some faint flicker of what it is like to be the universe. This position that consciousness is not exclusive to brains, but is a fundamental feature of any sufficiently integrated physical system, is called panpsychism, and it is no longer a fringe position. Philip Goff at Durham University, Christoph Koch at the Allen Institute, and Hedda Hassel-Murch at the University of Oslo are among the growing number of philosophers and scientists who argue that panpsychism is the most parsimonious solution to the hard problem of consciousness, the problem of explaining why physical processes give rise to subjective experience at all. If consciousness is fundamental, built into the fabric of reality at every level, like mass or charge or spin, then there is no hard problem, There is no magical threshold at which unconscious matter suddenly becomes conscious. Consciousness is always there. What changes is the degree of integration, the complexity of the experience, the richness of the phi. IIT is not physics. It is neuroscience and philosophy, but it connects to physics through its mathematical formalism and through its implications for quantum systems. And it provides a framework in which the question, is the universe conscious, is not a mystical speculation, but a scientific hypothesis with a potentially measurable answer. Now, let me bring in the traditions, because the question, what is being, has been asked before, long before, and the answers arrived at through radically different methods share a structure with the answers emerging from physics. Thomas Aquinas, the 13th century Dominican friar who synthesized Aristotelian philosophy with Christian theology, producing the most comprehensive philosophical system in Western history, argued that being esse is not a property of things. It is the most fundamental reality there is. Being is not something that things have. Being is what things participate in. God, for Aquinas, is not a being among beings, not the most powerful entity in the universe. God is being itself. Ipsum esse subsistens, the act of being, subsisting on its own, without any limitation, without any potentiality, without any admixture of non-being. Every created thing participates in being, receives being as a gift, borrows being from the source. But no created thing is being. Only God is being. This distinction maps onto quantum field theory with startling precision. The quantum field is not a particle among particles. The field is what particles participate in. The field is the ground of their being. Every electron, every quark, every photon exists because the corresponding field is excited, because the field has lent its energy to a particular pattern, a particular excitation, a particular thing. But the thing is not the field. The thing borrows from the field. The thing participates in the field. The field is the ground. The field is, in the Thomistic sense, the being in which things participate. Aquinas would not have identified the quantum field with God. He would have seen the field as a created thing, contingent, dependent, requiring a cause beyond itself. But the structure of the relationship between the ground and the participants, between being and beings, between the field and the excitations, is the same structure Aquinas described. And the deepest question in quantum field theory, why do the fields exist? Why do they have the values they have? Why is there something rather than nothing? Is the same question Aquinas was asking. His answer was God. Physics does not have an answer. Not yet. In Islamic philosophy, Ibn Sina, Avicenna, the 11th century Persian polymath, whose Book of Healing and Canon of Medicine shaped both Islamic and European thought for centuries, made a distinction that cuts to the heart of the quantum mystery. He distinguished between wajib al-wujud, necessary being, being that cannot not exist, being whose essence includes existence, and mumkin al-wujud, contingent being, being that could exist or not exist, being whose essence does not include existence and therefore requires a cause. Everything in the physical world, every particle, every field, every law of nature is mumkin al-wujud. It exists, but it does not have to exist. The electron could have a different mass. The electromagnetic force could have a different strength. The universe could have different laws entirely. The physical world is contingent. It is the way it is, but it could be otherwise. And contingent beings require a ground, a wajib al-wujud, a necessary being whose existence is not contingent on anything else. Quantum field theory encounters this contingency at every level. Why does the electron field have the coupling constant it has? Why does the Higgs field have the vacuum expectation value it has? Why are there 3 generations of matter and not 2 or 4? Why is the cosmological constant, the energy density of the vacuum, 10 to the minus 120 times smaller than the most natural theoretical prediction? This last number is often called the worst prediction in the history of physics. The theoretical calculation of vacuum energy, based on summing the zero-point energies of all quantum fields, yields a value that is 120 orders of magnitude larger than the observed value, 120 zeros. The discrepancy between prediction and measurement is not a factor of 2 or 10. It is a factor of 10 to the 120th power. Something is cancelling the vacuum energy with a precision of 120 decimal places. No one knows what, no one knows why. The standard model does not explain these values. It measures them. It takes them as given. They are free parameters, approximately 25 numbers that must be put into the equations by hand because the equations do not generate them. Each number is contingent. Each could, in principle, be different. And many of them appear to be fine-tuned, adjusted to values that, if they were even slightly different, would prevent the existence of atoms, stars, chemistry, or life. The strong nuclear force, for example, is calibrated with a precision of about 1%. If it were 2% stronger, all hydrogen would fuse into helium in the early universe, and there would be no water. If it were 5% weaker, deuterium would not form, nuclear fusion would not ignite in stars, and the universe would be dark and cold forever. The theory describes how the universe works. It does not explain why the universe works this way rather than some other way. Every parameter in the standard model is contingent. Every constant of nature is, as far as we know, arbitrary. The physical world in its totality is mumkin al-wujud. It exists, but it does not explain its own existence. This is not an argument for God. This is an observation about the structure of physics. Physics describes. It does not ground. It maps the territory. It does not explain why there is a territory. And Ibn Sina's distinction between necessary and contingent being a distinction made 1,000 years ago, in a language and a framework entirely alien to modern physics, captures this structural limitation with perfect precision. In Buddhism, Nagarjuna's Madhyamaka, the middle way, refuses both extremes. That things exist permanently and independently, eternalism, and that things do not exist at all, nihilism. The truth is the middle. Things exist conventionally, but not ultimately. They arise dependently, persist conditionally, and cease when conditions change. They are neither fully real in the sense of having independent, permanent existence, nor fully unreal in the sense of having no existence at all. They are something in between, something for which most languages do not have a word, something that the English word being does not adequately capture because being implies permanence, and the things Nagarjuna describes are impermanent. Something that the English word becoming approaches but does not reach because becoming implies a direction, and the things Nagarjuna describes have no inherent direction. They simply arise, persist, and cease. Quantum particles are precisely this. They arise from quantum fields. They persist for a time, nanoseconds for some, billions of years for others. They cease decaying, annihilating, being absorbed. They exist conventionally. They can be detected, measured, counted, manipulated, used to build technologies. But they do not exist ultimately. They have no independent substance, no fixed identity, no permanent nature. They are dependently arisen. The electron depends on the electron field, the Higgs field, for its mass, the electromagnetic field, for its interactions, and the weak field for its decay channels. Remove any of these dependencies and the electron as we know it ceases to exist. It is not a self-sufficient entity. It is a node in a web of mutual dependence, a process sustained by conditions, a conventionally real, ultimately empty phenomenon. The Higgs boson, discovered at CERN in 2012, after a 48-year search costing billions of dollars, is perhaps the most dramatic illustration of Nagarjuna's insight. It existed for approximately 10 to the minus 22 seconds before decaying, less than a trillionth of a second, less time than it takes light to cross a proton. It arose from the vacuum, excited by the collision energy of two protons traveling at 99.9999991% of the speed of light. It existed for an instant too brief for any process in the known universe to register directly, and it dissolved back into the field, into other particles, into other excitations, into other temporary patterns, being without permanence, existence without substance, form without self-nature. Nagarjuna would not have been surprised. This is exactly what he predicted 2,000 years before anyone had heard of quantum field theory. Everything is empty. Everything is dependently arisen. Everything is real conventionally, temporarily, conditionally, and nothing is ultimately, permanently, independently real. The Higgs boson was the Buddha's teaching, written in the language of particle physics, lasting for 10 to the minus 22 seconds before demonstrating impermanence in the most literal way imaginable. In Hinduism, the nature of ultimate reality is described as Sat Chit Ananda, being, Sat, consciousness, Chit, and bliss, Ananda. These are not three separate attributes glued together. They are three faces of one reality, three ways of apprehending the same indivisible Brahman. The way length, width, and height are three ways of measuring the same space. You cannot have being without consciousness, because a being that is not known, not experienced, not witnessed, not registered by any awareness, is indistinguishable from non-being. You cannot have consciousness without being, because awareness must be awareness of something, even if that something is awareness itself. And you cannot have either without Ananda, without the experiential quality, the felt sense, the intrinsic what it is like, because being and consciousness without quality would be abstractions, not realities. The Taittiriya Upanishad describes a journey inward through successive layers of reality, from the physical body, Annamaya, through the vital breath, Pranamaya, the mind, Manomaya, and knowledge, Vijnanamaya, to the innermost core of bliss, Anandamaya. At each level, the reality becomes more subtle, more unified, more fundamental. And at the core, at the level of Ananda, being and consciousness are no longer separate from each other or from the quality of experience. They are one. The Upanishadic sage does not discover God as an external being. The sage discovers Sat Chit Ananda as the ground of their own awareness. The observer discovers that the observer and the observed are not two. Physics has established that being in the physical sense is quantum fields, excitations, information, entanglement. The question of consciousness, whether it is fundamental or emergent, whether it connects to quantum mechanics through Penrose's microtubules, or Tononi's phi, or some mechanism not yet imagined, remains open. And the question of bliss, whether existence has a quality, a valence, or what it is like, is not a question physics can currently address. But the Vedantic claim that these three are inseparable, that you cannot have being without consciousness, that you cannot have consciousness without some form of experiential quality, is at least not contradicted by the physics we have reviewed. And the possibility that consciousness is fundamental rather than emergent, a possibility taken seriously by IIT, by OR, by panpsychism, by a growing minority of physicists and philosophers would, if confirmed, vindicate the Vedantic intuition that being and awareness are two faces of the same reality. Here is the honest assessment, the final one, the one that matters. There is no quantum law of being, no equation, no theorem, no experimentally confirmed principle that tells you what being is, why you exist, or what the universe means. Anyone who tells you otherwise is either confused or lying. But quantum physics has revealed something about the nature of existence that is genuinely revolutionary. And here is what it is. Being is not what you think, not solid, not permanent, not independent, not simple. Being is quantum fields, vibrating in a vacuum that is not empty. Being is excitations arising from potentials. Being is entangled states that cannot be divided without changing the whole. Being is measurement events that select one reality from many. Being is information. Being is relational. Being is processual. Being is in every rigorous sense that physics can establish more like a verb than a noun. The contemplative traditions said the same thing. In different languages, through different methods, from different starting points, they arrived at a convergent description. Being is not what it appears. The solid is not solid. The empty is not empty. The separate is not separate. The permanent is not permanent. And the observer is not passive. The observer participates in the constitution of what is observed. The convergence is structural. It is not causal. Physics did not confirm the religions. The religions did not predict the physics. But they map the same territory, the territory of existence itself, and their maps, drawn independently, share the same contours, the same mountains, the same valleys, the same rivers, different names, different legends, different compass roses, but the same geography. This could be coincidence. It could be that the human mind, when it investigates the nature of existence, whether through equations or through meditation, naturally generates certain patterns, and these patterns reflect the architecture of the mind rather than the architecture of reality. This is the skeptical position, and it is respectable. Or it could be that reality has a structure that is deep enough, consistent enough, and universal enough to be glimpsed from multiple directions. That the contemplatives and the physicists are not generating the same patterns through independent cognitive biases, but discovering the same truths through independent methods. That the map and the territory are, in some deep way, related. This is the hopeful position, and it is also respectable. I cannot tell you which is correct. No one can. The question lies beyond the reach of both physics and theology, in a territory where intellectual humility is the only honest posture. But I can tell you this: the question is real, the mystery is genuine, the convergence is documented, and the fact that 100-year-old physics experiment, the double-slit experiment, the measurement problem, the quantum vacuum can make you feel the same vertigo, that a 2,000-year-old Upanishad makes you feel that vertigo is not nothing. That vertigo is a signal that you are close to something that matters, something at the edge of what language can express and what the mind can hold. There is no quantum law of being, but there is a quantum mystery of being. And that mystery explored honestly, without shortcuts, without slogans, is more extraordinary than any law could be. The vacuum vibrates, the fields excite, the particles appear, the observer participates, the entanglement connects, and the question, what is this? What am I? Why is there something rather than nothing? Remains. Not as a failure of science, not as a gap waiting to be filled, but as the deepest feature of existence itself, the question that being asks of itself, the mystery that refuses to be solved, because the mystery is not a problem, it is the ground